want to oppose problem number 13.
Problem number 13, charge meter.
Okay, so then we want to oppose problem number 2.
Problem number 2. Problem number 2 accepted. So all 15 please send your email to write down the name of the deputy.先消毒一下，因为它有3个，现在可以。它是状况哪里？这个墙哦，状况。你要让助理先，你手机好了嘛，对不对？对。你先用那个只要水帮那个4老师消毒一下。对对对。应该没有其他的了嘛，就 OK 棒就好了嘛，就是先消毒一下，然后 OK 棒。用这个啦，用这个加布块，然后用胶带把蛋先推起来。那也没药，这里也没药，只能先简单消毒一下而已。这不行啊，这是酸的。对，这我看了那个。这个紧张。 有点高啊，这个地方稍微点一些。这个可以用，
这个是可以用，
对，这个是这个是可以，你就稍微弄一个，帮它擦一点点，这个是可以啊，你用你手。没有，这个应该看。
没有，我要整这个。这个剪刀的品质还不错。这个可以先帮我，我说干净的话，没有问题。
很逊啊！
最后呢，这好。
剪刀，
了解。
我把它剪掉了。
这你手有在
有
有上。这么长。
对。
那个那片在对折。
So can I?
Okay, yeah, you can start.
Okay. So I'm the reporter from TYPT and my name is Chen Shiwen. Today I'm going to report problem number 2, droplet microscope. First, this is our outline. First, we have problem statement and we show observation video. Then we have theory and then chapters of the discussion and our experiments and calculations. First is the problem statement. By looking through a single water droplet placed on a flat surface, one can observe that the droplet acts as an imaging system. Investigate the magnification and resolution of the sample length. So our main focus will be by changing the parameter. Then what will the magnification and the resolution will change. First is our observation video. Okay, so through our observation video, we can just observe that. So when I add more water into the ring, and it forms a lens. So the size of the graph paper, on the box, the square on the graph paper will become larger. Right. So first, we apply lens maker format. It forms like this, and this is our schematic diagram. So I have a platform and I have a little droplet. So since R2 is going to infinity, because it's flat, so we can rewrite our formula like this. Then we calculate the radius of curvature. So in our experiment, we want to know that in specific volume of our water is going to, can form what focal length of the lens. So we want to calculate the relevance between the radius of curvature, the ring radius, and our water body. So since it's hard for us to write R equals spot, so we just form our equation like this. Then the magnification. So we define the magnification as H object, H image over H object, and equals D image over D object. So what is H object, D object, H image, and D image is we show it here. So we can know that the magnification is the ratio of the image and the height of image and height of our object. So we can apply Gauss length formula, just like this, and this is the distance of object and distance of image. We can calculate the distance of image, and we can rewrite our formula to this and going to this. Okay, then the resolution. So when the light passes through a circular aperture, it generates a diffraction pattern like this, which we call airy disk. And when I have 2 or more light source, it will form like the brush like this or this. So we want to know if there are two light source or only one light source. So in this brush, it's hard for us to tell I have 2 light sources, and this is easy for us to tell. So what is the critical point that we can tell it? So we can apply gradient correlation. So since the diffraction has the amplitude of our light, so when the lightest part just go to the darkest part of another diffraction pattern, we just say that it's an radial correlation. So it's hard for us to say that it's 2 light sources. So we can define this as the minimum resolvable distance, and so by divided by the distance between the light source and the brick hole. So we can define that theta is the minimum resolvable angle, and lambda is the wavelength of our light, and p is the diameter of the lens aperture. So here's our overall experiment and parameters of discussion. So we want to measure the focal length of droplet length in different water volumes and room diameters. And we want to measure the magnification, resolution, and some bonus like distortion of the droplet length. And the parameters of our discussion is the water volume and ring diameter. Okay, so here's my first experiment schematic diagram of the device. So I have the light source, I have the ring diameters, and here's my droplet. And I have another platform here, and which we call this distance is our focal distance. So first we place a ring on the transparent plane and drop some water into the ring and form the lens. Then we turn the light on, the laser, so it's a parallel light source. And we move the screen till the light spot is the smallest and measure the distance. Okay, so here's our result. So we have 3 sizes of ring, which is 2.5, 3, and 5 millimeters of ring radius. And in 2.5 millimeter we have those water volume. And so in our result, we can know that a small variation of water volume, V and F can be regarded as a linear relationship. So why is small variation? Because we did it and we can't measure it if we add more, a lot of water, because the droplet will just grow. It can form the lens. And V and F has a negative correlation. And here's my schematic diagram of my second experiment. So I have a camera here, and I take a photo of this set. And here's my droplet lens set. So I have a droplet lens, I have a ring, and I drop water inside. So it forms the lens, and I have a graph paper under it. And notice that the thickness of droplet lens set is 4 millimeters, which I will use it to calculate further data. So here's my step. So same, I place a ring, I drop the water, and I take a picture and analyze it. And here's my method. So I use image J, and since I took the photo, so it forms like this, and we can just measure the size of the block just outside the ring, and the size of the block inside the ring that we feed through our lens. So we can tell our magnification square is the size of the block through the lens divided the size of the block. Why is square? because we define in our theory, we define our magnification as the height of our image and object. So, and this is area. So it's the magnification square. And this is my result. So I draw a graph like it's 1 over f to 1 over magnification, 1 over n. And we can say that it's regarded as a linear relationship. And we can know that the intercept of those graphs is close to 1. Now, this is my third experiment. So I place a camera on the top, and I have a droplet lens, and I have a graph paper. And the lens and the paper has a 50 centimeters the distance between it. And I have a pattern on the graph paper, which is shown like here. And in this experiment, we want to measure about the resolution. So same the step. And how we analyze it, we same use image J, and it forms a pattern. And when we just make it bigger, it looks like this. So here, we call it unresolvable. This we call it resolvable. But in the boundary, we can tell the minimum resolvable distance. And I have minimum resolvable distance, and I have the distance between the lens and the graph paper. So I can tell the angle. And this is our result. So we can see it's very like, we don't know what is really relative about like the volume and the angle, but still we revise it, we times it through the magnification, and it's a linear. So after revise, we know that the actual minimum resolvable distance to the minimum result is the we revise it from the actual distance to the image distance. And this is my last experiment. So we want to know the distortion. So I have a graph paper which goes like this, and this is how my camera looks. And here's the same step, but we only use the R equals 5 millimeters. And the method is, so it will form a pattern like this. And so I have a collaborate grid distance and a grid image distance. So we divide it, and we can know that the distortion. And this is our result. So we can know that there's no specific trend of the distortion. And at the very end, I have 25 to 30% of distortion. So here's our conclusion. And here's our conclusion. We just show in every experimental result. And we compare the result to the theory. So first is the water volume of the radius curvature. So we know that when R equals 2.5 millimeters, it's very like the same, but when the R goes larger, it's didn't. So we think it may be because we assume it as a sphere. Okay, then we compare the magnification of focal length distance. So why it was just like not quite fit? Because we guess it's because of the distortion. And the next is we compare the angular resolution of string radius. So we revise our theory from D to a D times the magnification, and we can see that in R equals to 25 is quite thick. So thanks for your attention.
So first I hear about the recorder presentation, and so first you can turn to page 4. Yes. Yes. So at this part, you just use the ring to control the diameter of the. Right. Okay. Then can you turn to? Okay. So can you tell me the difference between the optical resolution and the pixel resolution?
Okay. So optical resolution is how my image forms, but the pixel resolution is relative to like my screen or my CMOS in our camera. So it's quite different.
Okay, I understand. So you consider it's an optical resolution. Right. Okay. So in your magnification, you have what magnification do you consider? Is the angular magnification, the longitude magnification, or the transverse magnification?
The longitude magnification.
Okay, so do you concern the other two magnification will affect this phenomenon?
Sorry again?
Do you concern the other two kinds of magnification will affect?
No.
Okay, understand. And so can you turn to page 4?
Page 4?
Yes. No. So sorry, page 5. Yes. Yes. At this next. Yes. At this part, from this equation, do you concern that the droplet microscope is a sphere?
We consider it as a sphere in our theory model.
Okay, understand. So at this schematic of the diagram we discussed, the gray part is it a glass surface or is it just the ring that you concern?
No, it's a glass surface, and we consider as a sphere, which we no need to put the ring, but we assume that there's an arc for the ring, for ring diameter.
Understand. And I think that's about it.
Okay, so let's go to the next page. Our corner has image is prepared.
Okay, so honorable judges and fellow listeners, I'm the opponent for this problem statement, and I'm from the team relativity. And here's the problem statement. By looking through a single water droplet placed on a glass surface, you can observe that the droplet acts as an image system. So you have to investigate the magnification and resolution of such a lens. So here will be a summary of the report. So the reporter has used the theory of the let's make a formula, the curvature calculation, the contraction to consider about the resolution and also the arithmetics and the rate of deterioration to discuss about how the resolution, the condition of the resolution. And as the experiment that is concerned to use a diary to fix the diameter of the water water droplet, and also use a graph paper to investigate the magnification, and also a camera and image shade analysis for the resolution and the curvature of the droplet. And as for the barometers, they consider to use the water volume and ring diameter for the resolution part. And the result, they find out that the V and F is linear from the lens maker and Gauss formula, and also the one divided by M and 1 divided by F is linear. So as for the reporter, we consider he has a strength of complete qualitative phenomenon explanation on how to observe the spirit of the modeling part as the schematic of how they consider about the droplets. And also he has a lot of experiments to prove their assumption and find some linear conditions of different parameters. And also he has a fair quantitative comparison between the theory and experiment, and consider that as partly focused to discuss the magnification and resolution of this problem statement. And we also consider he has a simple explanation to the phenomenon. And as for the suggestion, we consider the measurement will be more optimized, because that normally one of the experiment assumption is that it has a part that is unabsorbable. But in such a condition, it means that it's because of their experiment that it needs to be a more optimized experiment for some other machines. Yes, and so they also have a lax experiment for experiment result, and maybe they have some analysis method for improve that. And for the discussion part, we consider that firstly we wanted to discuss is the simple physics explanation about that. In the page 4, they discuss about equation that is this, but normally that equation is discussed about a spherical condition. But in the condition with no gravity, this condition won't be fixed, so we consider we will discuss about this first. And secondly is the qualitative understanding about the lens maker condition, because normally if you put a water droplet on the surface, it may cause the lens maker condition to not fit in this condition, because lens maker this condition is meaning of the two fixed and with two spherical circle. And but if they put on a glass surface, this condition may be considered as also the aperture depth. And thirdly is the conceptual clarification of the spheric aberration that normally considered is the curvature, which causes the spheric aberration, which causes the solution, and the resolution and magnification to have some error rate. And also the quantitative modeling about the error rate and the setup of how they fix the diameter and curvature will also be one part to discuss, because that if they fix the diameter to use a ring to fix that, which means that there will be a certain depth till the glass surface. So which means that in such a condition, they also will be considered about the curvature will also be affected. Yes, and there will be my opponent discussion. And next will be the discussion. So just in French page 4 that you mentioned. Sorry. Yes, page 6.
For discussion, I just have wrong now. Like this is the radius, not that.
Okay, I understand. So you mean if you calculate all these experiments from the radius from here?
This R is the radius of curvature. This water problem, and this little R is the radius that we just said.
Okay, I understand what the reporter wants to clarify this condition, but normally do you consider that the glass surface is also considered in the water droplet magnification and resolution part, because it seems it's also a surface that.
Oh, okay. I didn't consider it, but I think it didn't affect very much, because in our experiment we use the very flat, so it didn't affect much.
Okay, so then you the blackboard. So the reason why I consider that the glass surface is one of the most important conditions, because that from all your modeling you have to use the lens maker formula, right? But normally lens maker formula is just discussed about two spheres like this, and normally they have two fixed ends to consider at this condition. But if you add a glass surface, like here is the surface of the platform of the surface, and the droplet microscope will be here. But normally, if you add the glass surface at here, then they won't have fixed end. You understand what I consider about?
So you mean we can't tell the second radius of curvature, right?
Yes, I consider that your method is truly well to quantify this experiment, that you have tried to optimize to the thinner of the glass surface, right?
Yes.
So I consider that truly is a well experiment consideration, but maybe you can consider this for qualifying of the Benson formula boundary condition.
Okay.
And secondly is that you consider that the depth of the glass will also affect the aperture depth of how you see the object you want to consider, and from what you have seen, it also will affect the resolution and magnification.
At the very first of our experiment, we didn't consider, but when we compared the experimental and the actual angular resolution, that we revised our theory, like this formula. So in times of magnification, that is caused by, like you said, is caused by the depth of this thing.
I understand what wants to include the information, and so as the opponent, I consider that the actual depth effect is not mainly the resolution, but will be the magnification, because that just normal simple physics explanation is that when you go to some swimming pool, you see something will be, yes, like you understand what I mean. Okay, I understand. Okay, so then can you do concern in your magnification about some errors such as the spheric aberrations or the chromatic aberrations?
I didn't really consider, but I think our errors we think that our errors is caused by the distortion I just mentioned in my experiment.
Okay, so do you just mainly observe the object in the middle of the part or the edge of the part?
The middle of the part.
Okay,
So we want to minimize the error like caused by the distortion.
okay, I understand. So what I mean this is because that there's some error calculation. It's firstly a spheric calculation is because that mainly if you measure the thing in the middle of the object, then the middle of the light will be like this, but at the edge it won't. We can't focus at this part. So the error part may be some errors to consider. And secondly is the chromatic aberrations, but as we have considered discussion, you have considered that we didn't consider the color resolution.
Yes.
Yeah, different color in resolution, right?
Right.
So which means that in this condition that the chromatic aberrations will be effect because of different wavelengths which cause the different resolutions.
So we just fix our light source as like this. So it's like 6 nanometers. The lambda equals this. If I didn't remember it wrong.
Okay.
So we fix.
I consider this is a little modified to this consideration because it's what I discussed is just mainly not meaning of prop set, mainly because of the spheric operations. And secondly is that in your experiment modeling you have used a ring to control the diameter of the ring. But do you consider that the depth of the ring will also affect the curvature of the droplet? Because like it seems like from your modeling you have just used a glass surface and on the droplet to concern this theoretical model, right? But in your experiment you have to use a ring for control the diameter, which means that there will also be depth to the droplet, right? So then in this condition, maybe the droplet will have some condition which cause the curvature to change.
Okay, so first we didn't consider the depth of the ring, that is our fault, but I don't think that it will really affect on the radius of curvature, since when we just since it's just like here. It may affect like this depth has some like water, so we have some errors of our water body in our calculation.
Okay, understand. So then can you turn to the page which you have discussed this the experiment part? Maybe experiment 2 or 3. Yes, so at this part you have controlled the volume of the droplet. So how do you control the volume for using the ring?
So in our observation, we can see in our observation video, we can see that we use dropper.
Yes.
So we use dropper, we can control the water volume.
So, understand. So they still may be a discussion is about that the volume and the radius of the radius of the rainfall affect this phenomenon, right? So now I want to ask the wider question is that because normally you are concerned that the bigger the droplet will cause you're concerned that the bigger the droplet will cause a smaller curvature, right? But then they will have a bigger resolution. Am I correct? Just the resolution will be more optimal. But as the curvature as you limited the amount of water droplet, then the curvature will also increase, right?
The curvature
Just reversely, if the water droplet is there is you add the bigger the droplet, the curvature will be smaller, but smaller droplet the curvature will be bigger, right?
no, since like we set ring here, and I have a droplet here. So this is my drop. This is my radius of curvature. Since I can set it like I have a sphere, and I cut the top part here. Here is my ring radius. Right. So if I just add my water, the ring radius is the same, but the bottom here is more. So the relevance between these two is as mentioned in this.
Okay, understand. So I mean now I want to discuss is not mainly for your experiment, but it's like what I mean is like if you just put a water droplet on a flat surface, then the bigger amount of water, then the curvature will decrease, right?
Yes.
But the magnification will also increase, right? The resolution will increase. So the bigger the droplet, the resolution will increase. But if the smaller the droplet, the resolution will decrease, but the magnification will increase.
Yes.
So how do you concern there's the best optimal conditions to control the magnification and resolution to be both in the most optimal conditions? Are you just tell your thoughts?
So my thoughts and our experimental results that we think our magnification time. So our magnification times my lab resolution. So I can have a formula. So we can calculate the maximum or the minimum part.
Okay. And I think the last question is can you turn to the page which have discussed about the resolution.
That's about the resolution.
Yeah. Sorry, back to that. Yeah, back to the pages. Yes, this page. That.
Okay, time is up. Normally you have 1 minute to calculate.
Okay, so for the summary of the report, we firstly discussed about the boundary conditions of the lens maker formula and calculate the curvature. And secondly is that the theorem we have discussed about the diffraction which used an area disk. And moreover, we also have discussed about different magnification and resolutions with different conditions, and find out that how the reporter has concerned how they concern the resolutions and the magnification, because it seems that the definition of resolutions and magnifications are varied. And thirdly, for the experiment, we are concerned that the different volume, and use the iron to fix the different same diameter will cause different curvature, and it's the experimental results for the reporter to observe. And lastly, we have discussed about the optimal method of the resolution and the magnification in such a condition of the bigger and smaller droplets.
Time's up. And review.
Don't you think that using an iron ring is appropriate? And what do you think you can exchange?
I think we can just use iron ring things. If we all use the iron ring, then we have some vibration. So we can test our experiments in the same condition. So I think it's a
different magnification and resolutions condition.
And can you summarize your analysis of resolution?
So since we found that resolution, it has to also consider the magnification. So we have to use it to calculate our resolution and revise it. And through the revise, and we found out that the theory fits our experiment result.
You mean the analyze one?
The resolution.
Okay, so I considered that the method they have used is mainly the fitting method because the resolution we have discussed previously is mainly what the reporter wanted to consider. So I think the method may fit, but there still can be some adjustments that we did.
Yeah, do you think that there will be a relationship between the magnitude and the resolution?
I think there's some relation between those two, but I didn't really calculate it out.
Okay, so since that the discussion we have previous mentioned is that the bigger droplet cause the better resolutions, but the smaller droplet cause the better magnification. So it seems that there are some optimal conditions to optimal these devices, but we didn't consider the best optimal method through our discussion and further.
How do you think about considering the camera's resolution?
So since in this graph, so we can know that we can see our pattern is like this, and the camera resolution is not quite big. So I can just tell
Because the
that.
camera's resolution can cause the resolution of the analyzer.
No, since the camera resolution is far bigger and smaller.
All then you have 2 minutes to prepare. You have 4 minutes to come.
to analyze this. And they didn't think about that the volume and the radius of curvature.
Okay, time is up. The reporter, you have 10 minutes to conclude.
So first is our concluding remarks, is our reporter summary. So first, our goal is to investigate the magnification and the resolution of the droplet lens, and we use lens maker formula, cos lens formula to calculate it. And we measure the focal length, magnification, resolution, and distortion. And there was a difference between our theory and our data because we consider the droplet being a sphere. But when the droplet becomes bigger, then it won't be like actually a sphere. Then this is our discussion summary. So first we discuss whether the flat surface will affect our resolution and magnification. And then we discuss about whether the depth of the ring will affect the curvature of the droplet. Then how we control the volume of the droplet and how the volume affects the magnification and the resolution and how to optimize it. And the smaller the droplet, the better resolution. And of course the magnification. So how do we optimize it? And whether the droplet will change the color of the light, but we use the same light source, so it didn't have to consider. And here's some concerns that have to be resolved. The result that the depth of the ring won't affect the curvature very much. It actually affects, but not much. So I think we can just ignore it. Then because we use the light source with a constant length of 46 nanometers. And the arrow ring could like show the variables, so it will be the optimal of the measure. And we decided the best method of measuring will be optimal resolution rather than pixel resolution. Thanks.
Okay. So we have 5 minutes for you to ask questions. I have a question for you. How you determine the magnification? Is determined by the image height versus the object height. How you determine your magnification?
So since I have the graph paper, so I can measure the length or the area of my paper, and I can measure it when I see it through the lens. So I can divide it, then I can get my magnification.
So the magnification is the property of the lens. So do the other two people agree with this definition?
Normally, the definition of magnification has been 3 is the transverse, angular, and longitude magnification. And for the reporter, he has just used he used the definite of the transverse magnification. So from the experiment, it seems that it's fitting to experiment setup.
Yes, I also agree with the reporter.
If you agree with this definition, you use lens maker equation to determine the object size and the image size.
I mean that you asked for the magnification. And I think that because we can just use a normal thing to a thing that has been magnified and to over the thing that haven't been magnified.
Okay, yes. By your definition, you place the object in different position, you will have different magnification. So how are you going to explain this?
I won't put the object in different position because I will just put it on the same side and just take a picture and just use ImageA to do that too.
Okay, thank you. How about the reporter?
So since in our experiment we set the distance between the graph paper and our lens is 4 millimeters. So we
Do you agree you put in different position the magnification would be different?
yes.
How about the
Yes, I concerned that it'll also be different because it's due to the longitude magnification. Like the different aspect to see the the object want to concern that the magnification will be different due to the definition of longitude definition, magnification.
But you agree with you put in different position, the magnification in his definition will be different. If this is the case, then your definition is not the real magnification, but its position.
Right, but in our theory part, at the very last that we just talk about our magnification at like 1 over magnification to 1 over f.
Magnification of a single lens is not defined by the lens maker equation. So you are using the wrong equation.
No,
The second one
we didn't use.
It's okay. The second question is, have you ever considered the deformation? You deviate away from the sphere. Is this an important factor?
Sorry, again.
Your water drop that deviate from a sphere. The deformation is an important factor to affecting your result.
I think it's important and it really affects. So we measured our magnification just at the very center part of my lens. So I want to, I
It's all
don't.
about the
You mean the deformation of the droplets? Oh, I concerned that the deformation of the droplets is firstly is that it will affect the resolution because it will absorb the light and make it lighter. So they, and secondly is that they will have some chromatic aberrations in such condition.
Clearly, it will influence the magnification because the outside, the differences between the outside, the out circle and the center is that the out circle will be very weird. The line won't be straight. The line will be like weird, but in the center will be very.
Okay, time is up. Let's prepare the final story.
Seven, 6, 7, 7, 7. And then let's go for the opponent. At 6, 6, at 7. And finally, let's go for the reviewer. 5, 5, 6, 5, 6. Thank you for